Hello everyone, my name is Kanush Shah and I will be presenting our paper Lightweight Apparel Classification with Residual and Inverted Residual Block-Based Architectures, authored by myself and Professor Prashantite Uppal. Apparel classification has a wide range of applications, from recommendation systems to consumer behavior analysis in e-commerce and in social media. Knowing the category of an apparel or clothing item can prove to be pivotal in these applications. Previous methods for classifying apparel can be categorized into low parameter, high parameter, and multitask learning methods. Low parameter methods focus on low latency applications where they tend to have around 10 million parameters. High parameter methods tend to have over 50 million parameters, goes up to 250 million parameters. Multitask learning methods learn for multiple problem statements and use the quality of embeddings to improve performance in all domains. So, multitask learning approaches in our problem statement use the category of the data, the attribute of the data, which would be whether a clothing item is checkered, striped, or is made out of fur, woolen, or and so on and so forth, and positional landmarks or bounding boxes of the clothing landmarks. So, in this specific domain of multitask learning and learning, hyperparameter models, we've seen that the models are trained for at least a few days or even weeks in some aspects. They leverage the capacity of the data, the additional data, to improve the embedding quality and hence they improve the performance. However, multitask learning has in the past struggled to generalize outside of the data set and transfer to other data. And this 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 also has the added issue of increasing model complexity in order to accommodate all of the data. So wa- uh, in our case, based on the type of data that is available, it's obvious to us that class imbalance is one of the largest issues in the data set, where some classes might have over 20,000 images and some classes might have less than 100 images as well. And 15 of the 50 categories lack uh, 15 of the 50 categories have sufficient data, whereas the remaining 35 lack the adequate data required, and we only have a few hundred images. Previous approaches in multitask learning effectively use the supplementary data, and the low and high parameter models for classification use sequential convolutional neural nets and do not use residual or inverted residual blocks, which have in the past generalized better. Hence, we attempt to leverage the high generalization capability of residual and inverted residual blocks to classify apparel at low latencies while trying to increase the accuracy at which we can uh, classify them. This would also allow us to apply it for a wider range of applications, from embedded systems to analysis or on social media would require low latency applications basically. And we ran experiments on some of the following models: uh, ResNet, ResNest, EfficientNet, EfficientNet weights, which were pre-trained with Noisy Student, and we also used those with category and attribute as an experiment. So the base models that we had mentioned earlier, which were ResNet and EfficientNet, were used for quickly tuning the hyperparameters since their size is not that large and they train much faster compared to their alternatives. In ResNest, for example, uses split attention blocks and requires a larger amount of time to train. And EfficientNet on Noisy Student, uh, we use a larger model for that as well, which meant that it wasn't really it wasn't possible for us to tune hyperparameters by iterating on that model. So we used a smaller model or something that it was based on in term when it comes to ResNet, which is based on ResNet D. So that's the general process that we follow. So efficient net B2 was the base model for efficient net B4 with noisy student. And efficient nets use inverted residual blocks where narrow blocks are connected by an intermediate wide block, contrast to ResNet, where you have a convolution block of one by one, so that you have wider blocks which are connected by narrow blocks. And the B0 is shown below, which was scaled up by compound scaling in order to obtain B2. Compound scaling is just a way to uniformly scale the depth, width, and resolution at the same time. So the B4, which was retrained on noisy student. So noisy student uses the concept of a teacher and student model, where the teacher model learns to classify based on labeled images and generates labels for unlabeled images, and then the student is trained on both the labeled images and soft pseudo labels based on the teacher. So the intuition is that the student should outperform the teacher, and this process can be iterated to improve the student's performance. We use the pre-trained weights from ImageNet classification. This is mainly due to the fact that previously it has been observed that noisy student pre-trained weights generalize easier as compared to those which are not. The next model that we use is ResNet D. ResNet D would keep the concept of skip connections introduced in ResNet, where you reduce the problem of vanishing gradings. However, ResNet D would also have a average pooling trick, so that you can consider the entire feature map, and 75% of the feature map or input feature map was actually ignored earlier in the original ResNet. ResNest is the model that we will attempt to train better using the hyperparameters from ResNet, and it involves the use of stacked split attention blocks, and we use a radix of 4. So the diagram that's shown in front of you is actually in cardinality major view, and the same ResNest can be restructured in radix major view so that it's CNN accelerated and we can make full use of the GPU. And it enables split attention across all the feature maps. So this is the main element that allows it to improve its performance. The dataset that we'll be training on contains roughly 200,000 high resolution images, 40,000 images each for the dev and test sets. There are 50 label categories, of which 15 have a few hundred images, as I mentioned before. Multitask learning approaches would use an additional 1000 attributes, which would be very sparse, and key point information would also supplement this. And in the past, we have seen that multitask learning approaches tend to outperform those which do not use multitask learning by around 3% or more on top for accuracy. So the experiments and hyperparameter tuning section, where we found that high dropout values are great, which is not surprising, along with regularization in the loss function, both used to reduce overfitting and improve generalization. And for training, we use SGD with momentum to initially converge or get closer to the the minima of loss function or the maxima of performance. And we continue to train with SGD without momentum in order to pinpoint the exact stopping point or the early stopping point where validation accuracy was the highest. So the results are as in front of you. We were able to improve on the low parameter methods by a whopping 4%, and we were able to even outperform the high parameter methods in the past, simply because the models generalize better and use residual blocks. However, we were unable to outperform previous methods that used multitask learning. When we used category and attributes, and we did not use positional data, just category and attributes. For efficient net before, it did provide comparable performance to the previous multitask learning approaches. Uh, yeah, and uh, res nest ran on just it takes just 6 milliseconds to run on a Tesla T4 and around 350 milliseconds on the CPU, and it has only 9 million parameters. EfficientNet B4 has 19 million parameters in contrast, and it runs in around 16 milliseconds, which is still 1.5 times faster than the previous models. ResNest is 4.5 times faster than some of the previous models. Limitations. So our paper did face a couple of limitations, mainly due to limitations in compute resources and certain limitations that resulted from this in terms of lacking in reproducibility. Our proposed ResNest model had to stop training before the second stage was complete, where only SGD was used, which means that there is a probability that it could improve even further, and we were not able to apply ResNest with multitask learning. However, I would like to mention that ResNest was able to get to around 94.3% accuracy. So it reached 94.42 in actuality after training a bit with SGD as well. But it reached 94.3% just via SGD with moment Adam in case of ResNest. I'm sorry. We used Adam in case of ResNest, and we used SGD with momentum in all other models. I did mention that earlier somewhere. Sorry. Yeah, but since ResNest has attention, we use Adam instead of SGD with momentum for it, and it was able to obtain a 94.3% accuracy nevertheless, which means that there is a small scope for improvement as well. Um, so to conclude, we were able to improve the state of the art for low parameter methods, slightly improve the state of the art for high parameter methods for apparel classification, and we were able to have comparable to state of the art results when we were using category as well as attributes, and we were not using clothing landmarks. It would be interesting in the future work to see what can be obtained from vision transformers and CNN models. Vision transformers would not be the best in terms of uh, this problem statement, mainly because of the lack of inductive bias, and it would require even more images, in my opinion, to generalize well. However, combined with CNN, I feel like the results could be interesting and might even surprise us. Thank you. That's been my time.